This is Honors Algebra 2 Pre-Calc. We are doing 2.3, which is Introduction to Functions. So I'm going to give you two definitions in the reverse order that the book does because I think that makes more sense. So let's first start talking about the word relation. So relation is such a generic word that I can't even give you the definition without using sort of a similar word to describe it, which is relationship. So a relation is a really generic term to describe any sort of relationship at all between two variables. Super generic. It's like as generic as the word car, right? So the set of all inputs, which is usually the x value, but sometimes it's t or some other letter, but usually it's x, is called the domain, and that's going to be a word that comes up a lot for us. The set of all outputs, which is usually y, but not always, is going to be called the range. So let's now talk about the definition of a function. So a function is a specific kind of relation. So just like I said, relation was a really generic word like car, function would be a specific kind of car, like a Subaru or a Toyota, or you could get really specific and talk about like a specific, Toyota Corolla or something, right? But a function is a specific kind of relation. It's a specific kind of relation that follows one rule. That one rule is that each domain value, right? So each domain value, which again, if it helps to think about it this way, domain values are the inputs. So each input is paired with exactly one range value, which would be output, right? So if that's true, then it's called a function, and we frequently see function abbreviated fxn. I realize there's no x in function, but I did not make up this abbreviation. It's actually a thing, just like I didn't make up the abbreviation of definition. So when I write fxn, I mean function. It's not just me, it's an actual math abbreviation. I know that that's not how function is spelled, but that is an accepted math abbreviation for function. So we're going to do a quick example. We're not going to call it example one. I just want to walk you through this. So I put two tables here, and I want one of them represents a function and one of them doesn't. They are both relations, because again, relation is literally any relationship between two variables. So remember, the one rule that makes something a function is that any x value you see, any input value, is matched with uniquely one output, okay? So what that ends up looking like fundamentally is no repeats in the domain values, no repeats in the x. Because if you look, a is not a function, and the reason that a is not a function, so not a function, I think I need to get new colorful markers because they're kind of dying. The reason a is not a function is because of these 2 points right here. Right? If you input 1, you could get two different outputs. You could input 1 and get 3, or you could input 1 and get 11. That's not a function. In order to get a function, any input I give you, there should be one unique right answer for the output. So if you look here, if I had said what's the output when I say 2, you would all answer 5. If I said what's the output when I put 5 in, you'd all say 7. If I said what's the output when I put -3, you'd all say 9. But if I asked you for the output when I say 1, there are two possible answers, and that makes this not a function. Okay? B is a function, right? So B is a function, and the reason that B is a function is that each one of these inputs has a unique output. Now, let me point out that they could be the same number. So actually, let me just to make my point, let me put a 4 here. So now 4 occurs twice in the outputs, right? But that doesn't matter because, again, if I give you an input, you should be able to give me the single correct answer for the output. So if I say, when I put in a 1, what do you get out? You would have to tell me 4. The fact that when I say if I put in a 2, what do I get out? You also answer 4 is irrelevant. The point is that for each input, there is a specific, unique output. When I say 1, you say 4. When I say 3, you say 2. When I say -4, you say 3. When I say 2, you say 4. There's no confusion. There are no different outputs for a single input. And that's what makes something a function. Now, the reason that that's relevant is that disproportionately everything we do moving forward, once you get to calculus, is going to be doing stuff with functions. And that's not always true. There are a few, we do some kinds of problems that don't involve functions, but you are going to use so many functions over the next 2 to 3 years, and then depending on what you choose to do in college, you might do a lot more math with functions. So it's going to be really important that we understand how these work, that we can spot them when we see them, because we are going to be mathing with them a lot. So let's actually walk through an example similar to this one. We'll do an E1 and a P1 that's similar to this, okay? And then we're going to talk about a thing called the vertical line test. All right. So for an E1, P1, the entire question is going to be, is it a function or not? That's the whole question, right? So, and then y. So just highlight y if it's not, right? So for E1, let's do A and B, and for E2, or for P1, come on brain, we'll do an A and a B. Okay, so I'm not gonna get super clever here. All right, cool. Just gonna make up some numbers. 1, 2, 8, 3, 1, 3, 7, 7, 2, negative 1, negative 2, negative 5. Cool. 0, 5, 5, 6, 2, 4, 8, negative 1, 5, and 3, 2. Great, okay. So E1 and P1, is it a function or not? And if not, highlight why it's not. Okay, so remember, fundamentally, what makes something not a function is if there is an x value that repeats, because that means that that x value is paired with more than one y value. So this one is a function, right? Because if you gave me an input, if you said, okay, Hogan, input is 1, I would be able to answer that the output has to be 0, right? If you said, hey, Hogan, the input's 8, I'd be like, cool, 8, output of 5. Hey, Hogan, the input's 2, boom, output's 5. B is not a function, and the reason it's not is because the 3 repeats, right? So x equals 3 has 2 outputs, and it's not supposed to have 2 outputs, right? It can only have 1 output. So if you plug in x is 3, you should only get 1 answer out, but if you plug x is 3 in, you could get one of 2 different answers. You could get a 6 or a 4, so it's not a function. So take a sec, try P1 if you want, or we can do it together. So pause me if you want to try it by yourself. So A is not a function, right? Why not? Because x equals 7 has 2 outputs, right? If you look right here, if you plug in 7, you get 2 different answers. And B is a function because there's no repeats in x, right? So again, if the x values repeat, you're looking at not a function, right? So that's pretty much it. Now let's talk about another way to spot a function. Sometimes we have a graph of a function. So if we're given a graph of a function, this is called the vertical line test. Because it's named after Mr. Vertical Line. No, I'm just kidding. It's actually Miss Vertical Line. Why are we so sexist? Totally kidding again. It's actually named because it's a test that involves drawing a vertical line. All right, so the vertical line test. Visually, a graph of a curve is a function if each vertical line, let's not even say each, let's say every vertical line intersects the curve at most once. And there's a more articulate version of this because I wasn't reading it. There is a more articulate version on page 103 if you want. So here's what we mean. This is y equals x squared. This is x equals y squared. This is y equals, it doesn't matter. I'm going to make up a fake curve. Okay, great. I made up some curves. Okay, so if we look at these graphs, right? If I were to draw vertical lines, infinite little vertical lines, see how each one of those hits the graph once? So what that means is that this thing is a function. Now, why does that make sense? Well, remember, what made something not a function was if one x value gave you multiple y value outputs. Well, if I draw So I'm just going to use this spot at x equals 2. If I draw a vertical line here, I hit two different y values. I hit a spot where y is, I didn't mean x is 2, I meant x is 4, my bad. I hit a spot where y is a positive 2, and I hit a spot where y is a negative 2. So one input of x, right? One input of x gives two outputs of y, right? So this is not a function, because if you can draw a vertical line and hit multiple spots on a curve, right? And that was just one spot. That was the example of where x is 4. But what if I could pick any spot. Look, fails the vertical line test. Fails the vertical line test. Fails the vertical line test, right? So anytime you can draw a vertical line and it hits 2 points or more points, like more than 2 points, what that's showing you is that one x value at whatever that vertical line is has multiple possible outputs. And remember, the definition of a function is that one input, one x, can only have a single output, okay? So if I try this one, right, if we try this one, all my vertical lines only hit once, so that's a function. Boy, I've really killed this orange marker. And then if I try this one, right, just pick any spot, right? This spot, this x value right here, whatever this has 3 possible outputs. So that is definitely not a function, because one input has 3 possible outputs, okay? So that's the vertical line test. Now, the vertical line test is most useful if you're looking at a graph of a function, because you can't possibly look, like if you have a graph, you can't make a table of every possible value of this function. That's not how it would work. If you're looking at a graph, you don't have a table, you visually look at the graph and you can see using the vertical line test if something is a function or not. So what we're going to do now is we'll do an HA2PC where we decide if the graph represents a function or not, okay? Cool. So again, function or not, and y. Okay. So for E2, I'm just going to draw you a couple graphs, and for P2, I'm going to draw you a couple graphs. So A and B and A and B. All right. So for this one, I'm going to draw this, and I'm going to draw this. Okay, and I'm going to draw this. And this. Cool. Okay, function or not, and why. All right, so I'm going to walk through E2. So remember that at most once. So over here, the vertical line doesn't hit anything. It's just hitting air. But here, it hits once, and it's going to hit once forever. So that's a function, right? All I need is one vertical line to fail. Pick one, any one. Oh, look, that fails. This is not a function, right? Because of this spot right here. That's my y, right? For this one, it goes on forever like this, but notice I'm only hitting once every time I draw a vertical line, so that's a function, right? And then for this one, all I need is one spot to fail, and it's not a function, okay? And that's pretty much it. The vertical line test is not going to require a ton of exposition. You're not going to have to, like, explain in sentences all that much. Okay, so one other thing I want to address that your book doesn't talk about real quickly, and then we're going to, and then we'll stop this video and I'll move on to domain and range in the next, okay, so before we cut this video, I want to talk about the phrase one-to-one function. So we've already talked about how a relation is a really generic term, right? So like, let's use an analogy for this, right? So like the word relation is like saying car, right? And the word function might be like saying Subaru, right? Which is a type of car. And the phrase one-to-one function, well, that's a more specific kind of function, like a Subaru Outback. So it's already a function. That's not how you spell Outback. Right? So it's already a function, right? So relation's a really generic word. Function is a more specific word that has some rules that go with it, right? And then one-to-one function is an even more specific. So it's already a type of function. You're talking about a function. So if a function is one-to-one, right, then not only do you have no repeats in x, but you also have no repeats in y. So a one-to-one function we already know that you can only have one y for each x, right? Now, a one-to-one function also only has one x for each y. So because it's a function, right, because it's a function, we know that each input, right, each domain value, right, has exactly one y, right, so one output or range value. Okay, but what makes it one-to-one, what makes it special and makes it one-to-one is that each output has exactly one input. Okay, so here's the idea. So this is sort of as a challenge because it's not a specific. That's not how you spell that word, guys. All right, so as a challenge, because this is actually not something specifically addressed in your book, pretty much at all, if I'm not mistaken. I don't think your book bothers to mention it at all. I don't think so. So, but it's going to come up, and it matters because sometimes when we talk about calculus stuff, certain things only work for the special kind of function that is one-to-one. So, is it one-to-one function? So, is it a one-to-one function? So, again, what we're talking about here, right? The shortcut here was no repeats in x, right? So no repeats in x is the fancy way to remember that, right? Sorry, inching over, my bad. Okay, well the shortcut here is that you can have no repeats in y, right? That's what this is saying. It's saying that you can't have multiple y's repeat either. So the easiest way to spot if something is one-to-one is just that neither the x's nor the y's repeat, right? So let's walk through this. So we basically have three options, right? We could have a function, we could have a relation, which is the most generic version where it's neither of the other two, it's not a function, or you could have a one-to-one function. So 1, 2, 3, 4, 5, 6. I'm the most creative person on the planet. 1, 2, 3, 4, 5, 4, and 1, 2, 2. 4, 5, 6. Great, I'm super creative. I'm not really. Okay, so remember, what it means to be a function is no repeats in x. So this one is definitely a function, and this one is also definitely a function, and this one is not a function. So this one's out of contention. I can go ahead and stop worrying about this guy right away because he's definitely not a function. So he's not one-to-one. So not a one-to-one function, okay? These are both functions, but this guy is a regular function, right? Because this output is matched with two different inputs. And this guy over here is a one-to-one function. Again, your book doesn't even address this as a thing, but it's going to come up as we move forward, and it would be doing a disservice to you to not pretend that that's a thing. This is also a really logical time to teach you what that phrase means. So, and here's the crazy part. If you stop and think, remember that things in math are named either after a person or named after exactly what they do, right? Pythagorean theorem is named after Pythagoras. Cool. Vertical line test is named because you're using a vertical line, right? Slope-intercept form is named because you have a slope and an intercept. Well, a one-to-one function is so named because it's saying that one x value matches one y value, and that's it. And one y value matches one x. 1, 2, 1. In both directions, one value matches the other value. There are no repeats. Once you see that, it's not a big deal. But again, when that comes up later in math, if you haven't been told the meaning, it's kind of a problem. So there you have it. Next video, we will talk some more about domain and range.